Okay, so when it comes to sequences, there is a natural question that we have to ask. And the question is, what happens to the terms of our sequence as n goes to infinity? As we look further and further down our sequence, will the terms be getting closer to a specific real value? And that is the idea of convergence. So we're always interested in the behavior of the sequence later on in the sequence, so when n is getting bigger and bigger and bigger. And that is the idea of convergence. So we simply write that the sequence an, n beginning from 1 to infinity, converges to L, where L is some real number, if, quite simply, the limit of the terms of our sequence as n goes to infinity is equal to L. So a very natural definition. We are asking, okay, as n gets bigger and bigger and bigger, as we look further and further down our sequence, what happens to the terms of our sequence? And all this means is when n approaches infinity, as n gets bigger, the terms of our sequence are getting closer and closer and closer to the fixed real number L. And when this limit exists, we say that the sequence converges to the real number L. We will sometimes write, instead of this, the more compact form an arrow L. When it comes to sequences, this means the same as this. So implicitly here we're looking at the terms of our sequence when n goes to infinity, and the terms are getting closer, they are approaching the real number L. That is the notion of convergence if this limit does not exist, which is possible, we say that our sequence diverges. So again, convergence means the limit makes sense, the limit does exist. So as n goes to infinity, the terms of our sequence are getting closer and closer to a fixed real value. If we say the sequence diverges, quite simply, the limit of the terms of our sequence as n goes to infinity does not exist. So our terms are not approaching a fixed real value. So very, again, intuitive definition. And let's look at, again, two graphical way of visualizing this idea of convergence, the sequence converging to a fixed real numbers. And the two ways are, of course, based on our previous video, where we looked at a sequence as a list of real numbers along the real axis, or as the graph of a function defined on the positive integers. So the first way to visualize convergence, suppose we say that the limit of our sequence as n goes to infinity is equal to L, and L is again a fixed real number. Just for argument's sake, I'll assume that the terms of our sequence are positive and that they are increasing, so they're getting bigger as n is getting bigger. Imagine that L is here, and now we're saying, okay, as n gets bigger, the terms of our sequence are getting closer and closer to L. So you could have a1 here, then a2 could be here, then a3, then a4, then a5, a6, a7, 8, 9, 10, 11, 12, and so forth. And as we look further and further down our sequence, a5, a6, 7, a1,000, a million, the terms are getting closer and closer and closer to the real number L. So that's one way of visualizing the sequence converging to the real number L. Now if we look at our sequence as now the graph of a function defined on the positive integers, we have an equally interesting picture. And again, we will make the same assumption here that the terms of our sequence are all positive and are increasing. We have our value L, our limit, which in this case becomes a horizontal asymptote. And you could have a1, then a2, then a3, then a4, a5, a6, a7, a8, a9, and so forth. And so you can see that in this way, we have the same intuition. As we look further and further down our sequence, the terms along the y-axis, the values of our sequence, are getting closer and closer and closer to the real number L. So two ways to visualize the same statement that the limit of a n as n goes to infinity is equal to L. And you can always choose the one that you're more comfortable with. Let's look now at a few examples of sequences, the same four that we looked at in our first video, and we will ask, in each case, does the sequence converge or does it diverge? And for simplicity, I'll choose this way of visualizing the convergence or divergence of the sequence, as it is slightly more compact than this way. It takes a little less space. But again, if you're more comfortable with this way of visualizing the convergence or divergence, then go ahead, no problem. So the question we're asking in each case will be whether the sequence converges or diverges. So if you recall, our first sequence from the previous video was n over 2n plus 3. As n begins from 1 and goes up to infinity, if you write the first few terms, then we had 1 over 5, 2 over 7, 3 over 9, 4 over 11, 5 over 13, and so forth. And now we're asking, well, as we look further and further down our sequence, are the terms of the sequence getting closer and closer and closer to a fixed real value? Well, let's see. Again, this is an, the nth term of our sequence, and we're looking at the limit as n goes to infinity of an n over 2n plus 3. We have an infinity over infinity case, but it's a simple rational function, and the largest power of n on top and on the bottom is 1, and if you recall, the simplest way of handling such a limit is to multiply top and bottom by 1 over n over itself. So 1 over n over 1 over n is just 1, but if we multiply through, let's see what happens. We'll have 1 on the numerator over, now 2n over n is 2, plus 3 times 1 over n is 3 over n, and the limit now is trivial. As n is getting bigger and bigger and bigger, 3 over n is getting smaller and smaller and smaller, and so it shrinks to 0. And in the limit, we're left with 1 over 2. And so indeed, the sequence converges to 1/2. So if you kept computing more and more and more terms of this sequence, you could use your calculator to get the decimals of these fractions, and they will get, as you look further and further down your sequence, the terms will be getting closer and closer to 1/2. So here the sequence converges. What was our second sequence? Well, if you recall, it was negative 1 to the n over 2 to the n, and again ranging from 1 to infinity. The first few terms are negative 1/2, positive 1/4, negative 1 over 8, 1 over 16, negative 1 over 32, and so forth. Before we look at the limit, let's visualize our sequence along the real axis. So we have 0. The first term is negative 1/2. The second term is positive, but half the size of the previous term. So this will be 1/4. The next term is negative, but half the size again of the previous term, 1 over 8. The next term is positive, but again half the size of the previous term. Negative 1 over 8. Positive 1 over 16. And the next term is again half the size of the previous term, but negative. Negative 1 over 32, and so forth. And you can see, at least guess, that the sequence seems to converge around 0. The terms oscillate from negative, positive, negative, positive, negative forever, but the oscillation about 0 is getting smaller and smaller and smaller, as each consecutive term is half the size of the previous term. So if we had to guess here, it looks like these terms are shrinking to 0. And again, the intuition is equally simple. If you say, well, what is our limit? Again, this is the nth term of our sequence. So negative 1 to the n over 2 to the n. And we have a rather simple case. Now negative 1 to the n will oscillate forever between positive and negative 1, depending on whether n is even or odd. So we can write plus or minus 1 over, as n goes to infinity, 2 to the n goes to infinity. So we have positive or negative 1 over something which blows up. So this will just shrink to 0. And so the limit does exist, n is equal to 0. And this is your value for L. And so our intuition was right on the money. As n gets bigger and bigger and bigger, the terms of our sequence are getting closer and closer and closer to 0. But they will always oscillate between positive and negative, but the oscillation will shrink to 0. What about our third example? The sequence negative 1 to the n going from 1 to infinity. This is a very simple sequence. Negative 1 plus 1, negative 1 plus 1, negative 1 plus 1, dot, dot, dot. And you can right away see that we have this oscillation that will go on forever. We'll always bounce back and forth between negative 1 and positive 1. And so if you look at this along the real line, so the first term of your sequence is negative 1, so you're here. Then the next term is 1, then it's negative 1, then it's 1, then it's negative 1, then it's 1, then it's negative 1. So we oscillate forever between 1 and negative 1. The question is, are we getting closer and closer to a fixed real number, a unique fixed real number? The answer is clearly no. We're just bouncing back and forth forever between negative 1 and 1, and so we are not approaching a unique real number, and so our limit does not exist. So if we look at the given sequence, the conclusion is that it simply diverges. As n is getting bigger and bigger and bigger, we are not approaching a unique real value. Let's now look at our last example. And if you recall, this was the sequence given by the root of n over the ln of n. And we began at 2 because the ln of 1 is 0, which would give us a division by 0, therefore would not exist. The first few terms, again, root of 2 over ln of 2, root of 3 over ln of 3, root of 4 over ln of 4, and so forth. So we're asking the same question. Does the sequence converge or diverge? So as we look further and further down our sequence, are we approaching a unique real value? Well, let's see. Now, this is not a trivial limit. If you look at the case that you're in, as n goes to infinity, both root of n and ln of n approach infinity. So you have an infinity over infinity case. Now you may be tempted here to say, well, since I have an infinity over infinity case, I can apply L'Hopital's rule, but you have to be careful. Here there is a small technicality. When you use L'Hopital's rule, you're taking the derivative of a differentiable function. But here, what we have is a discrete list of real numbers, not a continuous differentiable function. So you can't differentiate a sequence, as again, it is a discrete list of real numbers. It doesn't really have a derivative. But the idea is, this looks so much like a L'Hopital's rule problem. Can't we use L'Hopital's rule? The answer is yes, but we have to make a small change of variables. And the change is, we will always use n for a discrete variable, n equals 1, n equals 2, n equals 3, and so forth. If we want to use L'Hopital's rule, we want to differentiate differentiable functions of a continuous variable, and so instead of using n, we'll simply replace n by x. So ignore this for now, and look at the limit as x goes to infinity of root of x over ln of x. Now as x goes to infinity in a continuous fashion, whereas n goes to infinity in a discrete fashion, n equals 1, n equals 2, n equals 3, and so forth. Now here x tends to infinity continuously, and so root of x is a differentiable function of x, ln of x is a differentiable function of x, and now we can apply L'Hopital's rule. The derivative of root of x is 1 over 2 root of x over the derivative of ln of x, which is 1 over x, we can simplify this expression. We have 1 over 2 root of x, and if you divide by 1 over x, you multiply by the reciprocal, which is simply x. But x over root of x is root of x. So we have root of x over 2, and now the limit is trivial. As x goes to infinity, root of x goes to infinity over 2, which still goes to infinity. And so now you say, okay, well, if the continuous differentiable function, root of x over ln of x, approaches infinity, as x continuously approaches infinity, then the discrete version simply follows along for the ride. So because this limit blows up, this limit must also blow up. And our sequence diverges, right? The terms are getting bigger and bigger and bigger. Infinity is not a real number. So we can write here that as we move further and further down our sequence, the terms are approaching infinity, but make no mistake, the sequence still diverges. As n gets bigger, the terms of our sequence are also getting bigger and without bound. And that's it. Now, one last thing. The subtlety when we have the limit of a sequence, where we have a case where we want to use L'Hopital's rule, the change from a discrete variable to a continuous one, again, is a subtle point, and we'll look at this subtle point a little closer in our next video.